Are you aware of the history of coins? Do you know that coins were used to be made out of copper? Then time evolved and we started making coins out of silver. Now we even have coins made out of gold. A nuclear weapon called Little Boy was dropped at Hiroshima that had drastic effects. That was stuffed with uranium. Bronze medal. What do you think it is made of? Copper and tin. Now the question is, why we specifically used copper, silver and gold for a coin? Why uranium is used in nuclear weapons? And why in bronze, that is the metal, we use copper and tin? Now to understand that, we need to dive into these elements and look into their electronic arrangement. We need to know what energies are embedded in them. We need to know about their sizes, their masses, everything about them. Their reactivity towards air, water, and some important elements around us. So these are nothing but D and F block elements. So let's begin this journey of learning about them. So we have all seen periodic table, right? So in that we see when we go across a period, there is first of all S block, that is group 1 and group 2. Then we jump on to D block, group number 3 to group number 12. And then when we move ahead, we find the P block that goes from group number 13 to 18. And after that, in downwards, we find the F block. So we have all these sorts of blocks, right? So why do we name them as S, P, D and F? On the basis of electron entering in the last subshell. So when electron enters in D, that becomes a D block element. Now, here you see that when we go from S block, they are actually what? Most electropositive in nature. And when we move ahead, we are actually transitioning from electropositive species to electronegative species, which are P block. So this transitioning is happening because of D block, which falls in the middle. So that is why we also know them with the name as transition elements. And because they display metallic nature, we call them as transition metals. Now we have understood this about them. So do you notice when we are jumping to D, the first element is scandium, which is 21 in its atomic number. And that way we jump from calcium to scandium, we are entering into D. So there, when we pick the first element, that becomes scandium. And in that, from scandium to zinc, we have 10 elements for D. And similarly, when we go down the group, we again find 10 elements of D, again downwards and again downwards. We have 4 such groups. So let's try to understand first about their electronic arrangement, because everything starts with them. So first thing that we are aware is that atomic number, it is actually equals to what? The number of protons in it, and also equals to the number of electrons. Now, if we talk about their electronic arrangement, we need to know that, let's say I go for scandium, that is 21 in its atomic number. So when I fill electrons, they will go from 1s2, 2s2, 2p6, 3s2, 3p6, till now we are done with 18 electrons, and then comes 4s2 and 3d1. Now we are complete with 21 electrons. So we'll see that 1 electron has entered into the D, right? So that means we are started with the D block elements. Now if I go after scandium into the next element, that would be titanium, and that is 22 in its atomic number. That way, another electron will fall into D. So before that, what you need to analyze here is that D has 5 subshells. 1, 2, 3, 4 and 5. And in that, electrons which are possible are actually overall 10 of them. So maximum it can have 10 electrons. That is why we have 10 elements of D that goes along a period, right? So when I start with scandium, that is D1. When I go to titanium, there should be 2 electrons in it. So I would write here that there are 2 electrons. That is why the next configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d2. And further there will be D3, D4 and so on to D10. Now there's a problem while writing this like this. Why? So we cannot actually write it like this, that there is 4s2 3d1. We actually write it as 3d1 4s2. Why we do that? We are aware that there is, let's say this is your nucleus, and around that we have all these shells. So we know that we go from N1 to N2 to N3 and N4, right? So if this is my N1, this is 2, this is 3, this is 4. When electron is actually involved into any combination with any other species, so in that case, it is always involved from the outermost shell, not from the inner shell. That is why when these D block elements, they react, they actually take the outermost shell, which is the fourth. That is why we write that fourth in the end, not in the middle. So that is why 3D 4s2, not 4s2 3D, right? But remember that electron will actually enter into D only, which would be the third one, not the fourth one, right? So here we can actually replace this whole part of 18 electrons with argon, because we know that argon has a configuration of what? 18 electrons. So it is noble gas. So this is the configuration of argon. So rather than writing all of it again and again, we would just simply write argon, and with that we can write 4s2 3d2 for titanium. Then comes the vanadium, which would be your 4s2 3d3 and so on. So now when we move ahead into the complete table, so this is what? A 3D series. Why am I saying a 3D series? Because electrons are entering into third D. And we know when we go down the group, we find 4D because N increases. That means the principal shell. Then we will be having 5D. So that is why this is called a 3D series. And we will go downwards, we will find 4D, 5D and 6D. So here, if I completely fill all of these, we will see that scandium is what? 3D1 4s2. Titanium, 3d2, 4s2. Now you can get along with me and try to complete all of them. But remember, if I go to vanadium, it would be 3d3, 4s2. What will happen to chromium? You might think that it should be 3d4, 4s2. But that is not the case here. If you write it this way, it will be wrong. Why? Because what happens is that because this is chromium, and if I write it like this, 3d5, 4s1, it will be correct. Since we are aware, let's say you have this D, right? We have 5 subshells. Let's say you are 5 friends and 4 of you gets a chocolate and 1 of you doesn't get it. So that way, there is a possibility of having a fight. Now, if there is a possibility that the 5th one also gets 1 chocolate, you would all be very happy, right? So that is what happens with this chromium. Now, earlier, if I would give 4 electrons to it and this 4s is having 2 electrons, it won't be fair with this one. So there is a potential that there is a difference between them and there might be a fight. But if this electron, because they are having same energy, which is the 3d and 4s, not much of energy difference. So if there is a possibility that I give this 1 electron of 4s to this, which is the 3d, so all of them would be having 1 electron each and everybody would be happy. Now that is what happens in this case. So 1 electron will be here and 1 electron would be here. That is why when we write it as 3d5 4s1, not 3d4 4s2. So this is the correct configuration. Now when we move ahead with manganese, there is no problem with that. It would be 3d5 4s2. And when it comes to iron, it will be 3d6 4s2. Let's write it here. Then cobalt, it would be what? 3d7 4s2. Nickel, being the 28th element, it will be having 3d8 4s2. Copper. Now you might go ahead and write it 3d9 4s2. Now there's a problem again. We cannot write it like this. Why? That now you have these 5 friends again, and let's say 4 of them are having 2 chocolates each. One of them is only left with 1. So this 4s is also having 2 electrons. If I write it in the form of 3d9 4s2, this won't be a happy state for all of these. So if there is a potential and possibility that I give this 1 electron to this d9, it will become D10, and that would be a completely filled state. So I can just go ahead and write it like this. So you have this, and that's it. 3D10, 4s1. So this is the stable state for copper. Now, why am I saying that? Because what happens is that basically the half-filled and fully filled are more stable. So if there is a possibility for them to gain that stability, they would go ahead and do that happily, and that would actually bring them to a stable configuration. Now, there is a reason behind that. Basically, there is something called exchange energy when it comes to these species. So what happens is that now that I have two electrons each here, right? So electrons are what? They are not something that would be very stable or static. They cannot stay at one place. So they would keep on jumping from one state to another. Now, there are all these children, let's say, in a room, and you can't fix them with this place, and this place. They would keep on jumping from one place to another, but they would still be in the same room if you lock them there. So that is what happens with these electrons. They actually having the same energy between all the subshells of D. They jump from one subshell to another, then another to the first one. They keep on jumping like that, and that way they keep their energy to a stable level. So that is called exchange energy. So more is the exchange possible, more stability there will be. And that is the case for the D5, that means half-filled, and D10, which is the fully filled. So they have greater exchange energy. That is why they are more stable. So they prefer to take that stable configuration. Now this way, we actually go ahead and completely fill the rest of the teammates. So if this is zinc here, so that should be what? 3D10, 4s2. Now here there is no problem with zinc because this is what? Fully filled. And now this is the most happiest element. So there is one thing with this poor zinc. You have a lot of friends, and someone might think that they are friends to you, but they're actually not. So zinc, it actually considers itself to be a part of D block elements, but this is actually not a D block element. A lot of scientists do consider it a part of D block because it resembles a lot of properties of D block elements, but basically this is having completely filled D. And we said earlier that D block elements are the one which are actually having the unfilled D. Now, because it has all the electrons filled, it is not a part of D block element, but we keep it there because it resembles some of the properties. Now, moving ahead, if I talk about the rest of the teammates, so we will see that basically all of these are having these configurations similar to what we had in the 3D series. When we go downwards, 4D series will actually be the replicate of these, but the difference is now electrons are coming into 4D and 5s. Right, and same goes with the 5D series. So this would be the series and how electrons are being filled in the 4D and the 5D when we go down the group. Now think about the stability of their configuration and stability of their oxidation state. Once we have understood about the electronic configuration, electronic arrangement, we can go ahead and try to learn how they react, how they give electron, how they take electron, how happy they are to give electron or take electron. So in that process, when we move ahead, we look into the oxidation state of these elements. Now to learn that, basically they show variable oxidation state. Why they do that? So if we have this scandium, I know that its electronic configuration now is 3D1, 4s2. So here, what will happen? How many electrons it can actually give away? So basically, we can start by taking 2 electrons out from 4s, which is the outermost subshell, and then electrons can also be taken out of D because they have similar energy. Now, because of that reason, it can also show +2 as its oxidation state and also +3. So that way, it is showing variability in its oxidation state. It's not fixed that it will be 2 only or 3 only. It can also show +2 depending on the scenarios and also +3. Now, moving ahead, after scandium comes your titanium. That is 3D2, 4s2. Now here, it can give away its +2, that means the outermost 2 electrons, and also it can give away all 4 of them. And also, it can also give away its 3 electrons. So that way, it is showing variability in its oxidation state, and that is the case with all of the D block elements. Right, so now tell me which one is more stable state for scandium. So if it loses its all the 3 electrons, that would be more stable because that way we will end up having D0 and S0. which is very stable. Because now we do not have any fight between the rest of the teammates. D, if it is in +2, let's say, so that way it would be 3D1. And we know one electron in D is not stable because rest of the 4, which are the D subshells, they do not have even one electron and one gets one of it. So there is a difference in the energies now that would be created, which is not stable at all. Now, similarly, if I go ahead and move and check about all their oxidation state, I would find that scandium, it goes from +2 to +3 as its oxidation state. Titanium, it shows +2, +3 and +4. Now, the general electronic configuration was what? So, because I was having what? D going from 0, I would say actually from 1, because if it would be 0, it won't be a D block element. So I would go from D1 to D10, and S had already 2 electrons. So to generalize it, because D is on the inside and N had, that means the S had a greater value. So if this was 4 and this was 3, so can I generalize it and write over here instead of it N minus 1 and N. So this is the general electronic configuration, and on the basis of that only we are defining all the oxidation states. Now here, vanadium, what would be its electronic configuration? If you recall, it was D3S2. That means it is having overall 5 electrons. So all of these can actually go. So it can show +2, +3, +4 and +5. That would lead it to have a D0, which would be very stable. Similarly, when it comes to chromium, it goes from +2 to +6. And if I go ahead and check for all of their electronic configuration, and when we go down the group also, they would actually be similar. So here in 3D, we are going from +2 to +3 in scandium. Moving ahead, we reached till chromium, which was +2 to +6. Then +2 to +7 for manganese, which was D5 4s2. Moving ahead, likewise, the configuration actually changed because now we are having electrons being paired up. So greater the number of electrons now, so there will be a change into the oxidation state as well. So oxidation state will decrease when we go later into the group, right? So that is happening similarly in the 4D series and also in the 5D series. So these are all the electronic configuration and their oxidation state combined in one state. Now, what is the maximum oxidation state these elements can have? So one of the element which is called osmium, which is from the iron family, when we go down the group, we will find osmium there. So it shows +8 as its oxidation state. Now this much level of the variation they can actually show. So that goes from +2 to +8. So that way, if I ask you what would be the stability of oxidation state when we go down the group. So first of all, there will be 3D, then 4D and then 5D. So we know when we go down the group, radius increases and metallic character increases. So it is easy for 5D to lose electron, right? That is why higher oxidation state are more stable in your down the group. That means if I talk about the stability, so this should be the correct order, right? And moving ahead, if I ask you that this CrO42 negative, what happens to its reactivity as compared to the rest of the group? So when we go down the group from chromium, there is molybdenum and there is tungsten. So this is 3D, this is your 4D and this is your 5D series element. So when we go down the group, as we said, that stability of higher oxidation state increases. Now this oxide of chromium, which is this one. So in this case, the oxidation state of chromium is what? Let's try to find that out. So if I write it as X, 2X and oxygen offers -2. So -2 into 4, that would give me -8 equals to -2. X comes out to be +6. So chromium here is in +6 oxidation state and oxide of molybdenum and tungsten is also, let's say. So when we compare, the reactivity of tungsten will be less because its stability will be more because we are going down the group and it can hold greater oxidation state. That is why when we compare the reactivity of oxides of chromium, molybdenum and tungsten in +6 oxidation state, we will find that this is the stability order. And if I talk about their reactivity, so reactivity of chromium would be greater because this is more stable, so this would be more reactive. Moving ahead, if I ask you that there is 4D and 5D, so which one of them, because if I compare it with the 3D, so why 4D and 5D do not form stable ionic species? What happens is that when we talk about ionic species, so they're actually formed by the species which show low oxidation state. Because it is easier to give away 1 electron, 2 electron, 3, maybe I'll think about it, 4, okay. If I talk about giving away 5 electrons, that would be very difficult. Moving ahead, 6, 7, 8 electrons, not possible. So when the oxidation state increases, the higher oxidation state, so there the bond actually gains a covalent character. That means sharing. So they would not give 8 electrons, they would rather share them. And that sharing means that now the bond will be having a covalent nature. So that is why when we talk about 4D and 5D, which are stable in higher oxidation state, so they would rather go ahead and form covalent compounds, not ionic. So the reason is that they do not form stable ionic species because they prefer to show covalent character. Right, because they are more stable in their higher oxidation state. Now, let's say if I want to compare which one is more stable, titanium with +4 or titanium with +3. So here, first of all, we will get the answer from their electronic configuration. So basically, titanium +4 is actually D0. And if I talk about titanium +3, that is D1. So tell me which one will be having fight within itself. So that would be D1. So this is less stable state. So more stable would be D0 because now we do not have any electrons here. So we do not have anything to worry about. Now talking about manganese, so it is +2. And in +3 state, what will be its electronic configuration after the loss of 2 electrons? So in manganese, it would be D5, which is +2. And in +3, it will be D4. So clearly, D5 is what? It is half-filled. And half-filled are more stable. And more stable means, in this comparison, the one who's going to win would be manganese, which is +2 in its oxidation state. Now, this is all about the electronic configuration and the oxidation state of D block elements. Now that we have understood this, we can go ahead and learn about their radius and about their energies which they have. That means the ionization energy. And that all we will learn in the next lecture.